No class on Tuesday. At least I think that's how it works here. I think finals week there's no class. I hope so. Okay. So yeah, there'll be no class. So then you have a week just to go over stuff, and then if there's a real big problem with getting these solutions, the solutions to the third test posted, I'll probably just put it in an email and just send it out to everybody as a PDF. Okay. But I'm hoping it won't have to go that far. All right. So why don't we continue talking about 5.2 here for a minute. I'm going to mention a few things about some of your problems. This I could just have you do yourself, and I'm going to talk about this a little bit. I did last time, but if you remember number 2b, and I only did part of this, but part of this problem, okay, this is just a part of the problem, not the entire problem. Essentially amounts to you proving that 8 divides a to the 6th minus 1, right? We talked about this a little bit last time. So I guess the original problem was to show that a to the 6th is congruent to 1 modulo some bigger number, but the whole point is that you break the modulus down into its pairwise relatively prime pieces, right, by factoring, and then you just have to do it. You have to prove this result for each of those pieces and then put everything together at the end. Okay, and I gave you a hint. I kind of just did this off the top of my head, and actually it's a good hint because it works out pretty well. I'm going to tell you this just because I think this is actually really pretty cool solution. Okay, so a to the 6th minus 1 is the same thing as, I may have written this for you yesterday, a cubed squared minus 1 squared, right? That's for sure. Definitely true. This is a difference of squares, so you can factor this as a cubed plus 1 times a cubed minus 1. Yep, and I know I did this before. And I told you, some of you may have forgotten this, but I told you that both of these can be factored. Because both of these are, well, the first one is a sum of cubes, and the second is a difference of cubes, right? Because 1 is the same thing as 1 to the 3rd. So you can factor both of these, and if you forgot how to do it, nice thing is we have the internet now. You can easily just go on Google and say factoring sum of cubes or difference of cubes. You can get all these formulas in 3 seconds, right? So this actually factors as, the first part factors as a plus 1 times a squared minus a plus 1. Let's see if I get squeeze this in here. And the second factors is as a minus 1 times a squared plus a plus 1. Okay. Okay, so what was the assumption in the problem, which I didn't write this down, but the assumption, somebody can tell me if I screw this up because my book is closed, is that the beginning of the problem is that the GCD of a and 42 is equal to 1, right? Did I get that right? Okay. Now, and I think I mentioned this last time, but if a and 42 are relatively prime, that means that a can't be even, because then 2 would divide a, and 2, of course, divides 42. So the GCD couldn't be 1. It'd have to be at least 2. So a is odd, right? And again, I'm just jotting down notes here. So a is odd. Now, here's the idea. This is cool. All right. You want to prove that 8 divides a to the 6th minus 1. And we have a to the 6th minus 1 factored like this. You see that? Well, if a is odd, then a plus 1 is certainly even, right? And a minus 1 is even. And now think about this. I want you to think about this for a second. What do we know about a plus 1 and a minus 1? Well, A plus 1 is exactly 2 bigger than A minus 1. So these are consecutive even integers. Okay, think about pairs of consecutive even integers. 0, 2, 6, 8, 14, 16, 22, 24. One of them is divisible by 4. You can prove that, and you should, if you want to do it this way. That shouldn't, if you just doodle some examples, you should convince yourself pretty quickly that if you have a pair of consecutive even integers, one is divisible by 4. And you guys actually should all be able to prove that. If you have, basically what it boils down to is just, if the integer is even, start with the A minus 1, the smaller one. It's even, it's of the form 2k. Well, that k is either even or odd. If k is even, then it's of the form 4k, and then it's divisible by 4. If k is odd, then you add 2, and you get that it's divisible by 4. So one of them is divisible by 4. And again, this is something you guys should be able to prove. This is not that hard. So now think about this. And I'm not going to write anything else down. Think about this. They're both even. Both of these guys are even. And I'm telling you, one of them, at least, well, it's not going to be both, of course. Exactly one of them is divisible by 4. But the other one is still even. So you can extract an 8 from this expression. You see that? Slick. This is slick proof. So that's how you can do it.
Is that not how?
Oh, I don't know. This is probably. I mean, I don't know. I mean, I can't say that this is the best possible proof, but I can't imagine it gets much easier than this. This way, you avoid using the division algorithm, dividing by 8, and all that kind of nonsense. This way, you can just get it really quickly.
So why did you pull out the 8?
Because you're trying to prove that 8 divides a to the 6 minus 1. Don't forget what we're trying to prove. So one of these guys is divisible by 4, the other by 2. So we've got a 4k and say a 2l, so now we can get an 8 to be pulled out, so 8 divides the whole thing. Right? Does that make sense? Okay. So, fill in the details here. And yeah, the other part I think is just essentially just for Ma's theorem to get the other two factors, and then this is the one where you just kind of have to play with it a little bit till you see kind of how to proceed. But I just wanted to show this because I thought this was kind of a neat way to do it. Okay. Any questions about this one? Okay. Now, I'm also going to talk about a couple more of these. And again, I apologize again for kind of screwing things up on Tuesday. But actually, these problems all follow essentially the same format. And for the most part, there's not a whole lot going on with these. You just have to really notice one thing and then apply Fermat's theorem. And that'll solve almost every one of these. Almost every one of them. Except, I mean, here's an example where you actually had to use some trickery to get it to work out. But most of them just involve doing what I said. So let's see. Let me, everybody have this down now? We good? Okay, so let me talk about, I think maybe I feel like I started talking about this on Tuesday. 4D, show that a to the 9th is congruent to a mod 30, right, for every integer a. Okay. Two parts to this. And what I'm going to do here really will apply to more than just this problem. And we talked about this a little bit before. But first thing you want to do, and I know this is a little bit vague, but you want to take your congruent and you want to split it up into, okay, I'm just going to be informal here, into pieces by, sorry, okay, by factoring the modulus. Okay. So what do I mean by that? I just mean, right, I think I said this to you guys on Tuesday, if I'm not mistaken. But this is an if and only if 1, a to the 9th is congruent to a mod 2, 2, a to the 9th is congruent to a mod 3, and 3, a to the 9th is congruent to a mod 5. And I'm going to pause here because I want you guys to, I really encourage you to listen to what I'm going to say here in a second. This is almost as fundamental to doing these problems as the actual Fermat's theorem is, really. Okay, and actually, I think it was you, Matt, that asked about this sort of idea on Tuesday. So think about this. Just go back to the definition. This is nothing deep, really. It isn't. Just go back to the definition of congruences. What does this mean? It means that 30 divides a to the 9th minus a. That's what that means. Well, if 30 divides something, sorry, hang on. No. Okay. So if 30 divides a to the 9th minus 9, or sorry, a to the 9th minus a, then all the factors are going to divide it as well, right? 2, 3, and 5, okay? And conversely, if 2, 3, and 5 divide a to the 9th minus a, then by a theorem that we have talked about before, their product, because they're pairwise relatively prime, we can squish them all together and the product's going to divide it, right? Okay. So all we have to do now is establish these 3 different conditions. Okay? So what about number 1? How do we do that? Well, these now you just apply Fermat's theorem to. That's really what it boils down to. Okay, so the first one, or the corollary, right? A squared is congruent to a, right, mod 2. This is, actually it's a corollary, but this is, right, Fermat's theorem. So when you have this, remember this, for any prime p and any integer a to the p is congruent to a mod p, right? So once you've got this, well, what can you say? I'm not going to go through all of this, but you know, you can raise both sides to the 4th power, right? So what do we get? We get a to the 8th is congruent to a to the 4th mod 2, right? Okay, but from here, right, this is where we started. We know that a to the 4th, if we square both sides, right, a to the 4th is congruent to a squared mod 2. Does that make sense? So we know that a to the 8th is congruent to a to the 4th, which is congruent to a squared, which is congruent to a mod 2. And so I'm going to stop with this one, but you can see how this is going to play out probably. Once you know that a to the 8th is congruent to a mod 2, then a to the 9th is congruent to a squared, and a squared is congruent to a. basically the point is once you know that a squared is a, then a to everything is a. Basically, that's what it boils down to. Yeah.
I thought it was easier to understand what was going on by instead doing if a squared is congruent to a using formula 2e, we can multiply both of them by a to get a to the third is congruent to a squared. And repeat that process. A to the fourth is congruent to a to the third. Blah, 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 until you reach a to the 9.
Yeah, I mean, it's, yeah, I mean, either one is about more or less equivalent. So, yeah, you could do that too, for sure. Yeah. Yeah. Okay, so I'm going to sort of leave you to finish this yourself. But how do you do the mod 3 and the mod 5? It's the same thing. You just use, for the 3, just use the fact that a cubed is congruent to a by Fermat's theorem. And for 5, a to the 5th is congruent to a. And you just kind of like this. You just kind of mess with it, and it just falls out. And once you get all those 3 parts, then you get what you're looking for. Is this okay? Any questions here about this particular problem? No? Okay.
Will we see one of these on the exam?
It's possible. Yeah, it's possible. Okay. We okay then with this? Okay, so this is what you're doing for a lot of these problems is whatever your modulus is, you want to break it up and factor it into powers of products of primes, and then just attack each of those pieces individually using Fermat's theorem. And that applies to the vast majority of these. Let's see. So, for example, I'm going to do another one here. 6b. Okay. Is to show that a to the 5th and a have the same units digit. Okay. And this is going to follow basically the same thing. I actually have to deal with something real quick. I'll be right back. Okay, so and I think, yeah, there's no assumption on A here. This can be anything. Show that a to the 5th and a have the same units digit. So this goes something like this. have the same units digit, and we talked about this a little bit last time, if and only if. Okay, so remember what I said about the units digit, right? It's just what this is congruent to mod 10, reduced between 0 to 9, right? So this just means if a to the fifth and a have the same units digit, that means a to the fifth is congruent to, say, c, right? Mod 10. And a is also congruent to c, mod 10. And here, c is just some integer between 0 and 9. Okay, so remember, just think about this for a second. If we call c the units digit of a to the fifth, if we just call it c, right? It's some integer between 0 and 9. That's all it is, right? Then a to the fifth is congruent to c mod 10. And if a has the same units digit, then a is congruent to c mod 10. So what can we say about this? What can we conclude? A to the fifth. Sorry, I really mean an if and only if arrow here. If and only if a to the fifth is congruent to a mod 10. That's really what this problem boils down to now. And so if a to the fifth and a are the same modulo 10, that means they have the same units digit. Okay. So really, this is what you have to prove right here. A to the fifth is congruent to a mod 10. Then you're done. And so you go about this the same way we talked about with the other problem, right? You factor 10, 2 times 5. So you just want to show that a to the fifth is congruent to a mod 2, and a to the fifth is congruent to a mod 5. Okay, and again, remember, and this is really easy. A to the fifth congruent to a mod 5 is just Fermat's theorem, corollary to Fermat's theorem, right?
So we were trying to show that it was congruent to a mod 10 originally?
Yes.
That's it. So we broke it into 2 congruences by factoring the modules.
Mm-hmm. Yes.
And then we have to show that that's congruent to both of those.
You have to show that a to the fifth is congruent to a mod 2 and a to the fifth is congruent to a mod 5.
Okay.
Those are the 2 things you have to show.
Okay.
Yeah.
I apologize. I was just
No, it's okay.
confused.
That's the idea, yeah. And mod 2 is easy because a squared is congruent to a mod 2 by the corollary to Fermat's theorem. And again, remember, when a squared is the same as a, then a to any power is the same as a. So that's easy. The other part is just Fermat's theorem. That's easy. You're done. So there's not a whole lot going on here. Once you see how to, word the, how to attack it the appropriate way using these congruences, there's not much to do here, really. Okay, is this okay? Any questions? No? Okay. I'm going to talk about one more, and then I think I'm going to leave the rest to you to finish. But again, since you're not going to have solutions to this before the final, I thought it would be good to go through a few more than I normally would. So 10a says that you're trying to prove something. So it says to prove the following thing. Prove if a to the p is congruent to b to the p mod p, then a is congruent to b mod p. Okay, sorry, this thing is, I got to straighten this out. Okay. So this is kind of interesting. It says that you can cancel the p out in some sense. P's a prime, of course, in this case. So this is really all it boils down to. There's not a whole lot going on here. You are not, some of you might think that you want to just use the definition and go back to the definition of a congruence and say, okay, P divides A to the P minus B to the P, then P divides A minus B, and just do it directly, or try to do it just from the definition of congruence. You don't want to do that. You want to use the stuff that you have at your disposal from this section to do this. And so what you want to note is that A to the P is congruent to A, right, mod P. And B to the P is congruent to B mod P. And this is just from Fermat's theorem, right?
Could you state the original problem again?
Prove that if A to the P is congruent to B to the P mod P, then A is congruent to B mod P.
Okay.
So, and this is all there is to it. And you're invoking some theorems, an earlier theorem on congruences that basically say you can kind of change the order around certain ways. But A is congruent to A to the P, right? That's a property we know. We can flip the order. And by assumption, A to the P is congruent to B to the P, right? That's our assumption in the problem. We know that B to the P, over on the right-hand side, this is congruent to B mod P. And there you go. You're done. Use the transitive property of congruence, and you get that A is congruent to B mod P.
I have a question.
Yes?
Wasn't there maybe I remember this wrong, but wasn't there also something in the theory, one of the basic theorems you gave us, that said A to the K is congruent to B to the K mod P? You could raise it to a power. You could raise both of them to a power.
Yes.
So couldn't you just use that?
No, you're confusing it with the converse. If A is congruent to B mod n, then A to the K is congruent to B to the K mod n. But it does not say that if A to the K is congruent to B to the K mod n, then A is congruent to B mod n.
You can go up, but you can't go down.
It's an if-then statement. It's not an if and only if statement. Right.
The reason that is because it has to be raised to a positive power.
In fact, there was a question on the third exam that said, true or false, if A squared is congruent to B squared mod n, then A is congruent to B mod n. False. Not true. Choose A to be 4 and B to be 2. Doesn't work. Yes?
In the directions, for some reason, I bring up the fact that assuming that bank theory is not divisible by the quantity.
Right.
Like
No, I think that's just for the other part of the problem. Here you don't need it. You don't need it in this part. Because, what we used, A to the P congruent to A and B to the P congruent to B are true for any values of A and B. Yeah. But the last part, I'm guessing, is where that comes into play, probably. Okay. So really, you've got to, I think I've showed you all the tools, really, that you need to finish up the rest of the homework here. So I'm not going to do the rest of these for you. But it's really, these problems are not that bad once you just see what it is you're supposed to do. Okay. So anyone want to ask any questions about some earlier stuff, or would like to see a problem from, I don't know, maybe an induction problem or something like that? I mean, this is up to you guys now. Now I've done my piece here. If you want to ask about stuff, feel free to. Yeah.
Okay. We were told that we were not going to have to prove anything that was shown to us in the class. We can already use
Right.
those.
Yes. Mm-hmm.
Which essentially covers pretty much any main theorems that were in the book.
Right.
With that said, unless the problem is specifically directly from a homework problem, can we do that same thing? Like there was a homework problem that we used to solve this, so I'm using that.
Oh. Yeah, I see what you're saying. I don't think that is even going. I know what you're worried about here, but I don't think that's even going to come up on the exam. So the problems that you're going to have to use, I mean, really, these are just things that are going to follow from, basic theorems in the section and such. And so, if there's any possible confusion, I'll make some note about it in the directions. But yeah, I know what you're asking, but it's not really going to come up. Okay. Yes.
So we just do, I don't know, like chapter 1 to number 10. It's an induction for
Okay.
greater or less than or equal to.
Okay. Let's see.
It was a homework problem, but.
Chapter 1, number 10. Okay. Is it 1.1? Yeah, okay. Okay.
Some page 7.
Yeah, I see it. Okay. So this is page 7 of your text. Okay, 10A. Yeah, so there are several different kinds of induction problems. You should be familiar with all of them, really. Okay, so is less than or equal to 2 minus 1 over n. All right. Okay, now this is actually a good one because this, what I'm going to do when I write the solution out here is, this is not going to be totally polished, but I'm going to do this in the way that I think the train of thought should sort of progress as you go through this problem. Okay. You're trying to prove this is true for every positive integer n. So remember, what you want to do is, there are 2 steps that you need to follow here. So the first thing you need to establish is so-called base case, right? And that is, you want to prove that, or verify that, if you will, 1 over 1 squared is less than or equal to 2 minus 1 over 1, right? That's the base case. N is 1, so there's only one term on the left-hand side, and so it just reduces to this. And then what is this? This is just 1 is less than or equal to 1, which is true. Okay? So this is really just, this first part really is obvious. Okay. And the second is the inductive step. Okay, the inductive step then is when you assume that whatever it is you're trying to prove is true for some positive integer n, and you want to establish the same assertion for n plus 1, right? Assume for some natural number n that 1 over 1 squared plus 1 over 2 squared plus on down to 1 over n squared is less than or equal to 2 minus 1 over n, right? And you want to prove that this same inequality is true with n replaced with n plus 1, essentially, right? So let's just, this is our inductive hypothesis. That's what this is called. Put a little asterisk next to this. And what we have to prove, this is what we're allowed to assume. What we have to prove then.
Are you sure it's for some?
Yes. Well, you never write assume for every n and n, because then you've assumed exactly what it is you're trying to prove. You never would write assume for every n and n that this is true, because it's like saying prove Fermat's last theorem. I'm assuming Fermat's last theorem, therefore it's true. You don't do that. Okay? So what we have to prove is we just keep going, right? Keep going. And instead of stopping at n, we stop at n plus 1 instead, right? 1 over n plus 1 squared. And we have to prove that this is less than or equal to 2 minus 1 over n plus 1. Okay? Now, the idea behind induction is that you want to take your inductive hypothesis and you want to mess with it until you get what it is you're trying to prove. Okay? So, here's the idea, really. What you're assuming for some n, this is your starting point, and you want to get here. You don't want to start, and some of you were doing this before. You're starting with what you want to prove, and then doing some stuff to that. No. Logic, that's not right, really. You start with what you assume, and you get to the end, to where you need to go, right? If you start with what you're trying to prove, then you've tacitly assumed what it is you're trying to prove to be true. If you're working with it, maybe it's not true. Maybe it doesn't even exist. That's what you have to establish. You can't get your hands on what you want to prove until you start with the inductive hypothesis and get there through logical steps. Okay? That's the thing I want to stress about induction. Do not mess with what you're trying to prove. Start with what you assume to get there. Okay? So that's the biggest slip up I've seen when we were doing this before. So,
one minor point.
Yeah. Mm-hmm.
From our assumption,
Mm-hmm.
you said that we were essentially trying to prove replacing n with n plus 1.
Sort of. I mean, that's not exactly right, but
Okay, so
you're not, I mean, if you were just literally replacing n with n plus 1, then you wouldn't have an n. Then you would have skipped from n minus 1 to n plus 1. So I didn't really mean it that way. I just mean the statement, which is going up to n, instead go up to n plus 1.
so I guess my question at this point,
Mm-hmm.
even though like sometimes I do it and it works,
Mhm.
why are you adding an extra term on the left side if you don't have an extra term on the right side?
Because, okay, look at the original statement here. Here's our original statement that we're trying to prove. So, if I were to call this inequality P of n, well, notice, okay, this is probably a better way to say it. This guy right here and this guy right here are the same. So if I'm going to n plus 1, it still has to have the same form. So this guy right here and this guy right here are going to have to be the same. Right? I mean, just imagine that n was 4, right? Then the assertion would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared is less than or equal to 2 minus 1 over 4, right? So it's wherever you end up is less than or equal to 2 minus 1 over wherever you ended up. That's exactly what the assertion is saying. Okay? So what do? Well, we need to get to this point, and this has a 1 over n plus 1 squared that this doesn't have. So why don't we just add 1 over n plus 1 squared to both sides of this, right? I'm not going to write that down, but that's what I'm doing right now. So okay. I just took our inequality that we're starting with, and I added 1 over n plus 1 squared to both sides of it. That's where that's how I got from here down to here. Okay. Well, now this is why I said I'm going to do this a little bit more informally. What is it that we'd really like to be true in order to finish the proof here? Here, and this is where I want you to listen to this for a second. Okay, this is important. This is what we have right now. So what we're trying to prove, we have the left-hand side of the inequality right here. But we do not have the right-hand side. This is different than this. Okay? So what I would really like to show now, if possible, and think about this for a second, think about it. I really would like to show that whatever this is is less than or equal to this. Because if I can do that, then think about it. Then we've got what we want on the left-hand side, less than or equal to this, and if I can show that this is less than or equal to this, then by transitivity, this is less than or equal to that. And that's exactly what I want to show. That should be your thought process here at this point. So now your goal should be to prove that 2 minus 1 over n plus 1 over n plus 1 squared is less than or equal to 2 minus 1 over n plus 1. Yes?
Is it redundant to put the less than or equal? Could you just say less than, because there's no way those terms would be equals?
Yeah, I mean, well, I mean, you're not really gaining anything by this, really. And in fact, maybe they are the same, because you can cancel out the 2's, and it's not, I mean, they're not, but let me put it this way, you're not gaining anything by doing that. You might just end up being wrong. So since you only have to prove less than or equal to anyways, why not just leave it there? You see what I'm saying? Okay. Okay, so this is now what you have to show, is this. And now here's where, this is what you would do now, this is what you would do on scratch paper. And then you would work your argument backwards in your solution. Okay? Well, what is this equivalent to? Well, the 2's, we can certainly cancel the 2's on both sides, right? So this is really equivalent to just minus 1 over n plus 1 over n plus 1 squared less than or equal to minus 1 over n plus 1, right? And from here, basically what you're going to do is you're just going to keep sort of messing with this until it gets down to something that is obviously true, and then you work your argument backwards. Okay. Okay. Well, maybe we don't want these negatives. So we can rewrite this as, okay, sorry, I'm running out of room here. 1 over n plus 1 plus 1 over n plus 1 squared less than or equal to 1 over n. Okay, sorry, this is getting really... But you see what I did? I just brought the 1 over n plus 1 over to this side. The 1 over n I brought over to the other side.
You have thought about reciprocating the entire expression? Would that be...
Well, that's not really going to get you anything here, because the reciprocal of sum of two reciprocals, you can't just cancel the reciprocal out. 1 over a plus 1 over b is not a plus b. Okay, I think that's what you're saying. Just take the reciprocal, and then I get n plus 1 squared less than or equal to n, or something like that. But that's not the reciprocal when you have two fractions. Okay. But
if you did it term-wise, that doesn't work?
No. So, I mean, for example, 1 is less than or equal to 2. If you take the reciprocals, then then is 1 over 1 less than or equal to 1/2? No, it's not. Right? Reciprocals in general are only going to flip things, but when you've got sums and things like this, yeah, you can't just take reciprocals and just hope things are going to work out. They generally don't. Okay, so what can we do with this? I don't know if you guys want me to finish this or not. I don't know. So what you could do here is combine these into one fraction, right? Get a common denominator just by multiplying the top and bottom of this guy by n plus 1, by 1 over n plus 1 by n plus 1. And then you can cross multiply from there. Okay, well, I'll go ahead and finish it since we're so close anyways. Okay, so what we had was, sorry, 1 over n plus 1 plus 1 over n plus 1 squared. What was it, less than or equal to, what did we have? 1 over n. Okay. Again, this is what we're ultimately going to try to prove this. Well, if we get a common denominator, this is the same thing as n plus 1 over n plus 1 squared, less than or equal to 1 over n. Okay? See what I did here? I just multiplied the first fraction, top and bottom, by n plus 1. Okay. And now, let's just clear the fractions here. Now let's multiply everything through by n times n plus 1 squared. Both sides. We can do that. It's positive. We don't have to worry about flipping inequality signs. Then what do you get? Well, the n plus 1 squared is going to cancel, and then you're still going to have an n here, and then it'll be n plus 1, right? Less than or equal to, on the other side, it'll be n plus 1 squared left over, right? Because the n will cancel with the other n. Okay, so now you can see how this is going in your mind, right? You just keep going with this. N squared. Okay, so this just becomes n plus 2. So this is n squared plus 2n less than or equal to n squared plus 2n plus 1. See that? And that is definitely true. How would a really good proof proceed then? Okay, here. Let me just, I want you guys to keep in mind, this is important. I want to make sure you didn't forget this. I'm not saying that this is the right way to establish the proof. I'm saying this is what you do on scratch paper, and you say, I got to prove this. Well, this is equivalent. I mean, actually, in this case, you could do this because these are all if and only ifs. In general, you may not be able to do that. But, well, what's this equivalent to? This is really is equivalent to the following simple assertion: 0 less than or equal to 1. And that is definitely true. So how would a nice proof proceed through this? We would start here and would go backwards. Now, in this case, and I'm being a little more liberal now with the if and only if arrows. If you want to establish something and everything you have is literally equivalent to what you're writing down after it, you can just do if and only if, if and only if, if and only if, if and only if, and get down to the end like this. That's fine. That's okay. So the proof really hinged on simply the fact that 0 is less than or equal to 1. That's it. Okay, well, this one is a little trickier, maybe than some of the other ones were, but I would say the majority of the induction problems probably are not quite this messy. Other questions? Diane, you look like you wanted to ask something.
I was just trying to see one that maybe wouldn't be as messy, but anything from the binomial.
Okay, binomial theorem section.
I know.
Okay.
This a long time ago.
Okay. Sure. Let's see here. Okay, so I'll just remind you of this real quick. And this is the form the book gives it in. Okay, so yeah, just due to time here, I'm probably not going to do a long problem. I'm going to remind you of the binomial theorem and then kind of the thought process. And I'm probably going to do a fairly short one this time. Okay, so binomial theorem says that a plus b to the n is equal to the sum from 0 to n of n choose k, a to the n minus k, b to the k. Okay, so
You said b to the k?
yes.
So the coefficient of each term is just that n choose k,
Mhm,
right?
that's right. Yeah.
I remember because I lost.
Yeah. No. Yeah. That's right. Okay. 3D says to show that this might jog your memory. I may have even done this one for you before. I don't remember. But n choose 0 plus. Oh no. Let me see. Is that what I want to do? No. Sorry. Let's do 3B instead. Okay. Yeah. Okay. Sorry. So minus. N choose 1 plus n choose 2. This is really messy. I'm sorry. Minus, and then you just keep on going. And at the very end, it's plus minus 1 to the n times n choose n. And the point is that this is equal to 0, I guess. Right? Yes. Okay. And the point is to prove this by using the binomial theorem. Okay. Well, here's what you do. Here's the idea. Now, this one actually happens to be maybe a little easier than some of the other ones. But the idea here is look at your sum, and all you're doing here is you're just trying to choose a and b appropriately so that when you expand out a plus b to the n, using the binomial theorem, you get exactly that. Okay? And so, first of all, whatever your expansion is, this needs to be equal to 0. And remember, if you look at the binomial theorem, the coefficients of all these powers are of the form n choose k, right? And all of these coefficients here are either 1 or minus 1. They're all either 1 or minus 1. Okay, so yeah, so then sorry, that's not what I meant to say. I mean, the coefficients actually go up. I mean, we see these n choose k, these binomial coefficients coming up throughout the expression here. It's just that they also have either a 1 or a minus 1 on the outside. Okay?
In the A and B terms?
No, I mean, if you look here, look at the n choose k in the binomial theorem. We have all of these things here, except the signs are alternating. That's all I'm saying. The signs are alternating, right? If we want this to be equal to 0, then we want, if we're going to use the binomial theorem and want everything to collapse to 0, then a plus b should be 0. Okay? And notice that we also don't have any a's or b's or anything. It's always just either 1 or minus 1. So the most natural thing to try first then is just to choose, for example, a to be 1 and b to be minus 1. And then expand it out using the binomial theorem. Okay. And then just follow the reasoning here. 0 is certainly, whatever n is, 0 is certainly 1 plus minus 1 to the n. You should all buy that. Doesn't matter what n is, right? 1 plus minus 1 is 0. 0 to any power is 0. And now this is where we use the binomial theorem. And now I'm just going to write all the terms out as we go up. Where do we start in the binomial theorem? Well, k equals 0, right? So it's n choose 0, 1 to the n minus 0 times minus 1 to the 0. And what is, I'm not going to write that all down, but if you just follow along here, all you're doing is you're now using the right-hand side of the binomial theorem. The sum from 0 to n choose k, a to the n minus k, b to the k. Well, we start with 0. A is 1 and b is minus 1. So this, since a and b are both 1 or minus 1, this product here has to be either 1 or minus 1. Has to be, always. Okay? And so we're just going to be left with, in this case, because we're raising minus 1 to the 0, it's 1. So the coefficient is just 1 and choose 0. And that's exactly the first term that we want. What happens if we plug in 1 for k? Well, again, the a part look at the binomial theorem. The A is 1. It's always going to be 1, so we don't have to think about that. If we plug in 1 for k for the b term, since b is minus 1, we're going to get minus 1 to the first, right, which is minus 1. So then the second term will just be minus and choose 1. The minus comes from the fact that minus 1 is being raised to the first power. And then we just keep doing it, right? And this just continues all the way down to the end. And that's it. So all you're doing, once you identify A and B, you just plug them into the theorem and just write the expression out. Instead of the sigma notation, just write it out, and that's it. Okay, I think probably have to stop because I have to hand your homework back as well before you go. Okay, so what I've decided to do is this homework. Man, I've been really nice to you guys lately because I have all this trauma occur to me, and I haven't had time to do my job as well as I should have. So I gave you a completion grade on this one as well. Okay. Now, before the final, you will have some of these. I'm going to pick a few of these to write up solutions to. So you'll still have. So let me say it this way. There was another assignment I gave you a completion grade for, although online I wrote up solutions to 3 problems. Those are fair game in the graded homework portion of the exam. Okay, even though it wasn't graded, that's still fair game. All of these things that you see online that I have solutions for, those are fair game. Okay. All right.
When would you expect the servers to work?
Knowing this. Now, here's the idea. This is cool. All right. You want to prove that 8 divides 8 to the 6 minus 1. And we have 8 to the 6 minus 1 factored like this. See that? Well, if A is odd, then A plus 1 is certainly even, right? And A minus 1 is even. And now think about this. I want you to think about this for a second. What do we know about A plus 1 and A minus 1? Well, A plus 1 is exactly 2 bigger than A minus 1. So these are consecutive even integers. Okay, think about pairs of consecutive even integers. 0, 2, 6, 8, 14, 16, 22, 24. One of them is divisible by 4. You can prove that, and you should, if you want to do it this way. That shouldn't, if you just doodle some examples, you should convince yourself pretty quickly that if you have a pair of consecutive even integers, one is divisible by 4. And you guys actually should all be able to prove that. If you have, basically what it boils down to is just, if the integers even, start with the A minus 1, the smaller one. It's even, it's of the form 2k. Well, that k is either even or odd. If k is even, then it's of the form 4k, and then it's divisible by 4. If k is odd, then you add 2, and you get. Nice thing is we have the internet now. You can easily just go on Google and say factoring sum of cubes or difference of cubes. You can get all these formulas in 3 seconds, right? So this actually factors as, the first part factors as a plus 1 times a squared minus a plus 1. Let's see if I get it. Squeeze this in here. And the second factors is as a minus 1 times a squared plus a plus 1. Okay. Okay, so what was the assumption in the problem, which I didn't write this down, but the assumption, somebody can tell me if I screw this up because my book is closed, is that the beginning of the problem is that the GCD of A and 42 is equal to 1, right? Did I get that right? Okay. Now, and I think I mentioned this last time, but if A and 42 are relatively prime, that means that A can't be even, because then 2 would divide A, and 2, of course, divides 42. So the GCD couldn't be 1. It'd have to be at least 2. So A is odd, right? And again, I'm just jotting down notes here. So A is odd. So I guess the original problem was to show that A to the 6th is congruent to 1 modulo some bigger number. But the whole point is that you break the modulus down into its pairwise relatively prime pieces, right, by factoring, and then you just have to do it. You have to prove this result for each of those pieces and then put everything together at the end. Okay, and I gave you a hint. I kind of just did this off the top of my head, and it's a good hint because it works out pretty well. I'm going to tell you this just because I think this is actually a really pretty cool solution. Okay, so A to the 6th minus 1 is the same thing as, I may have written this for you yesterday, A cubed squared minus 1 squared, right? That's for sure. Definitely true. This is a difference of squares, so you can factor this as A cubed plus 1 times A cubed minus 1. Yep, and I know I did this before. And I told you, some of you may have forgotten this, but I told you that both of these can be factored. Because both of these are, well, the first one is a sum of cubes, and the second is a difference of cubes, right? Because 1 is the same thing as 1 to the 3rd. So you can factor both of these, and if you forgot how to do it, that is divisible by 4. So one of them is divisible by 4. And again, this is something you guys should be able to prove. This is not that hard. So now think about this. And I'm not going to write anything else down. Think about this. They're both even. Both of these guys are even. And I'm telling you, one of them, at least, well, it's not going to be both, of course. Exactly one of them is divisible by 4. But the other one is still even. So you can extract an 8 from this expression. You see that? Slick. This is slick proof. So that's how you can do it.
Is that not how?
Oh, I don't know. This is probably. I mean, I don't know. I mean, I can't say that this is the best possible proof, but I can't imagine it gets much easier than this. This way, you avoid using the division algorithm, dividing by 8, and all that kind of nonsense. This way, you can just get it really quickly.
So why did you pull out that 8?
Because you're trying to prove that 8 divides A to the 6 minus 1. Don't forget what we're trying to prove. So one of these guys is divisible by 4, the other by 2. So we've got a 4K and say a 2L, so now we can get an 8 to be pulled out, so 8 divides the whole thing. Right? Does that make sense? Okay. So, fill in the details here. And no class on Tuesday. At least I think that's how it works here. I think finals week there's no class. I hope so. Okay. So yeah, there'll be no class. So then you have a week just to go over stuff, and then if there's a real big problem with getting these solutions, the solutions to the third test posted, I'll probably just put it in an email and just send it out to everybody as a PDF. Okay. But I'm hoping it won't have to go that far. All right. So why don't we continue talking about 5.2 here for a minute. I'm going to mention a few things about some of your problems. This I could just have you do yourself, and I'm going to talk about this a little bit. I did last time, but if you remember number 2b, and I only did part of this, but part of this problem, okay, this is just a part of the problem, not the entire problem. Essentially amounts to you proving that 8 divides A to the 6th minus 1, right? We talked about this a little bit last time.